Hello everyone. In this video, we are going to look at each and every calculation in the regression output in Microsoft Excel in a systematic fashion. So this is the typical summary output that we get out of regression analysis when we use the Excel's data analysis toolpack. So the first thing that we are interested in is the beta coefficients. In our data set, we have one regressor, which is the TV advertising budget, and one dependent variable, sales. So we are getting two beta coefficients out of the regression analysis. As soon as we get the beta coefficients, we can calculate the predicted Y and the residuals. So let's do that. Predicted Y is given as intercept, fix that, plus slope, fix that, times X. So this is the Y hat, or the predicted Y, and the residual is simply actual Y minus the predicted Y. Alright, the next thing we need to do is to calculate the average value of X and average value of Y in the sample. We will use these averages in various calculations later on. So to find out the average value of X, we go average of X vector, and I'll just drag it and it will calculate the average Y for me. So here, one of the important properties of OLS estimates is that the OLS line actually passes through the sample averages as well. That means the sample average X bar and Y bar will lie on the OLS line. So if I take the average of the predicted Ys, it should match with the average of the actual Ys. So let's verify that. Average of predicted Ys, it's same as the average of the actual Ys. And the average of the residuals is 0. So let's verify that. Residuals is 0. Alright. Next, let's look at this output section right here. The first one says multiple R, which is 0.7822. This is really nothing but the correlation between X and Y. So let's verify that. Correlation X comma Y, and we match the result. Now here I took the correlation between X and Y. We can also find the correlation between Y and Y hat, or predicted Y, and it will be the same. The reason is Y hat is a perfect linear function of X, right? So let's calculate the correlation between Y and Y hat, and it's the same. Now the reason I did find the correlation between Y and Y hat is because in case of multiple linear regression with more than, let's say, 2 regressors, there are many X, right? But there's only one predicted Y. So in case of multiple linear regression, the multiple R would be the correlation between Y and Y hat. Alright, so next is R square. R square is the square of the correlation between X and Y. In case of multiple linear regression, R square will be the square of the correlation between Y and Y hat. So let's verify that. Here is the correlation square, and that's our R square, and it matches the output. Next, we have adjusted R square. Now adjusted R square is crucial for multiple linear regression where we have many regressors, right? So let's calculate this. 1 minus R square times n minus 1. So n is the number of observations. In our case, the number of observations is 200. So 200 minus 1 divided by n minus k minus 1. So again 200 minus k. K in our case is 1 because the number of regressors is 1 because this is a simple linear regression problem. So 1 again minus 1. Now that's our adjusted R square figure, which matches the output. Next, we can calculate the standard error, but I'll come to that because before we calculate the standard error of regression, we need to calculate the various sum of squares, right? So let's do that. So if you look at the ANOVA table here, it actually tells you how much of variation of y comes from what source. All right. So the first one is explained sum of square, also called as sum of square of regression, is given as the total sum of squares of the predicted y's from the mean y. All right. So let's calculate that. One quick note before we calculate the explained sum of squares. Notice that the average value of the predicted y coincides with the average value of the actual y. All right. So this is sum of squares. Inside of this function, I will pass the predicted y's minus y hat, right? Fix y hat. Now I will press Control Shift Enter. So that's 3314.61 and that matches with the output right here. All right. So basically I'm using an array calculation. The value of y hat will be taken one by one, but the distance will be taken from the fixed y hat. And then it will be passed as an array to the sum_sq function, which will return the sum of square of these deviations. Next, let's calculate the sum of squared residuals. This is pretty straightforward. We have the residual values. All we need to do is find out the sum of squared residuals. So I'll use the same function, sum_sq, and I'll pass the residual vector. Enter. And this is 2102.53, which matches with the output. And the last piece is sum of total squares, which is the sum of squared deviations of actual y from the mean y. All right, so let's use sum_sq. Inside of this, I'll pass the actual y, which is my sales vector, minus y hat. Y hat is fixed. Bracket close, Control Shift Enter. That's 5417.14, which matches the result here in the table. Next, let's calculate the standard error of regression, which is nothing but the estimation of the standard deviation of the error term. And that's given as square root of the sum of square residuals divided by the degrees of freedom of the residuals. So this is equal to square root of SSR, we already calculated SSR here, divided by n minus k minus 1, which is 200 minus number of regressions is 1, again minus 1. Bracket close, enter. 3.2587, that's the standard error. So it matches the result. Next, let's look at the degrees of freedom. So if we look at the y vector, the y vector has n minus 1 degrees of freedom because we have n number of observations, but we are calculating y hat as the estimate for mean of y. So there we lose 1 degree of freedom. Residuals have n minus k minus 1 degrees of freedom. So basically we have n residuals, but not all n residuals are free. There are k plus 1 number of constraints on the residual vector. And what are those k plus 1 constraints? So one constraint is that the sum of residuals has to be 0. That is the property of OLS. The other k constraints are basically the fact that the residual vector has zero sample correlation with all the k regressors. So that's why the residual vector has n minus k minus 1 degrees of freedom. And the total has to match up to n minus 1, so regression has k degrees of freedom. So if you add the degrees of freedom of regression and residual, then you get n minus 1. So in our case, because n is 200, we get these degrees of freedom for these three items. Now we can calculate the mean squares. So we have the sum of squares. When we divide sum of squares by the degrees of freedom, we get the mean squares. So let's look at the first one, which is the mean square for regression, and that is equal to sum of square of regression divided by the degrees of freedom. 3314.62, which matches the output. And the second one is the mean square for residuals. So that is equal to sum of square of residuals divided by the degrees of freedom. 10.6188. Mean square is the same as variance calculation. We can also calculate the mean square for y. So that will be sum of total squares divided by the degrees of freedom. Alright, and if you look carefully, the square root of mean square for residuals will be the same as the standard error of regression. So let's quickly verify that. Square root of mean square residual is nothing but the standard error of regression. Next, we can calculate the Fstatistic. Now, if you recall, Fstatistic is used to perform a joint hypothesis on all the beta coefficients for the regressors, not the intercept. And it does so by comparing the variance between the restricted model and the unrestricted model. In our case, we only have one regressor. So the restricted model would be that if we don't include that regressor, so just the intercept, what will be the sum of square residuals? And that will be SST, the total sum of squares. If we use the regressor, then our updated SSR, which is the SSR of the unrestricted model, is nothing but the residual sum of squares that we have here, right? Using those two, we calculate the Fstatistic as per this formula. So let's go ahead and do that. This is equal to sum of total squares, which is the same as the sum of squared residuals for the restricted model, which only includes the intercept. So this is equal to, let me start the bracket, SST minus, for the unrestricted model, the residuals sum of squares will reduce. So this is this, and then divided by the same thing again, whole divided by, so let me put another bracket here, divided by n minus k minus 1, which is 198, bracket close, 312.144, and that matches the output. And immediately we can calculate the p-value for this test statistic. So this gives us the overall significance of the model. All right, so we can do that by looking at the F distribution. So this F statistic comes from this distribution. All right, so from this distribution we can calculate the probability to the right of this test statistic, which is the significance of this statistic. So this is equal to, I'll use F distribution right. So Excel thankfully gives us this direct formula to calculate the right probability to a particular value in an F distribution. So the value we are looking at is this, comma, there are two degrees of freedom. The degree of freedom of the numerator is k, which in our case is just 1, comma, degree of freedom of the denominator is n minus k minus 1, which in our case is 198. Enter. So this is the p-value or the significance of the F statistic, which matches the result. And this is highly significant. That means our regressor is significant. Now let's look at the table below here. We already know the coefficients. That's the starting point. The next thing we are going to calculate is the standard errors on the beta coefficients. Now, in order to do that, I prefer to do it in using the matrix formula. That's very efficient, and it really doesn't matter how many regressors you have, it will always work. And not only that, on top of variance, you also get the covariances. So I prefer that. So in order to use the matrix formula for variance of the OLS estimates, we have to use X, which is the design matrix. So we have to first build the design matrix. And it's not that difficult. All we need to do is append a column, which is vector of 1s, next to our regressor. So I create this matrix, which is our design matrix, and I have renamed that as X, so I can use it directly in the matrix calculation. And the variance covariance matrix for the two beta coefficients, that is beta 0 and beta 1, will be a 2 by 2 matrix. So I'll highlight these 4 cells and equal to, we have the estimate for sigma square, which is this square. Let me put a bracket here. Then multiplied by X transpose X inverse. So let me start minverse, which stands for matrix inverse, X M mult, that is matrix multiplication of X transpose X. So first transpose of X, then X, bracket close, bracket close. I have to press Control Shift Enter because the output is an array. So here I get the variance covariance matrix of the beta estimates. Now, as far as standard errors are concerned, we are only looking at square root of variance terms, which are in the diagonal, main diagonal. So just to verify, if we want to find out the standard error for the intercept, what we need to do is square root of variance of the intercept, which matches the result. And for the slope coefficient, we need to do the same thing, square root of the variance of the slope coefficient. And this matches the result. On top of that, if you need the covariance, it's here and it has to be same. The variance covariance matrix is always symmetric. After finding out the standard errors, we can talk about the hypothesis testing. Now recall that in hypothesis testing, we are trying to test if the coefficients are significantly different from 0. So the hypothesized mean for these two coefficients, the intercept and the slope coefficient, are 0. So the t-test is simply given as the estimated coefficient from the sample divided by the standard error. So let's calculate those. Coefficient divided by standard error. Coefficient divided by standard error. So you can see these results match with the output right here. Now, whether or not these t statistics lie within the zone of rejection or in the safe zone, for that we need to find out the critical values first. Here we are doing a two-tailed hypothesis testing. So in the t distribution, we have to keep 2.5% probability on either side, assuming that our level of significance is 5%. So let's calculate the critical values for the zone of rejection. On the right hand side, we can do t inverse probability. So when we use t inverse, it basically calculates the CDF inverse. That means if we are trying to keep 2.5% probability on the right hand side, the CDF, which is the left tail probability at that point, would be 97.5%. So let's use that, 97.5%. And T distribution has one additional parameter, which is the degree of freedom. Here, the degrees of freedom would be n minus 2, which is n minus k minus 1 basically, and here k is 1, so we have n minus 2. And this is number of observations, 200 minus 2. 1.972 is the critical value on the right hand side. And we can easily see that the t statistic that we got from the sample far exceeds this critical value, so we reject the null. That means the beta coefficients that we got are significant, and so the variable is also significant. Similarly, we can calculate the critical value on the left hand side, and that's given as T inverse. The probability would be the left tail probability, which is 2.5%, comma, degree of freedom is 200 minus 2, minus 1.97, and it is symmetric. T distribution is symmetric around the mean, so that's why we get the same number but with negative sign. So if the t-stat falls within the critical values, then we do not reject the null. If the t-stat falls outside the critical values, then we reject the null. We can also make the same decision based on p-value. What is p-value? P-value is the probability of observing t-stat more extreme than what we observed in the sample. In our case, both the t statistics are positive, so we can compare the area to the right of the t-stat against 2.5%, and if it is smaller than 2.5%, then we reject the null. Instead of comparing the right area against 2.5%, we actually compare double the right area against 5%, which is the level of significance. So let's do that step by step. For the intercept, the area to the right of the t-stat is given as t distribution right, this is the t-stat, comma, degree of freedom is 200 minus 2. Similarly, for the regressor, the area to the right is t distribution right, this is the t-stat, comma, 200 minus 2. Now this is the right tail area, but p-value in case of two-tailed hypothesis is essentially double the either the right tail area or the left tail area, depending on if t-stat is positive or negative. So here p-value would be twice these areas. And you can see that these results match the output. After getting the p-values, all we need to do is compare it with the level of significance. As these two p-values are extremely small, so it's very, very small than 5%, that means these are significant. We can also create confidence intervals for the population parameters beta 0 and beta 1. So we have the estimates of the parameters, and using these estimates and the fact that the estimates follow t distribution, we can calculate the lower bound and upper bound of the confidence intervals. Let's assume that we want to build a 95% confidence interval for the parameters. So for beta 0, the lower bound would be the estimate of beta 0 of the sample, then plus the standard error times t inverse probability I want to keep on the left hand side is 2.5%, comma, degree of freedom is 200 minus 2. Alright, similarly the upper bound would be the estimate. In fact, let me copy paste this same expression with a little bit of tweaks. Estimate plus standard error times t inverse. The area to the left would be 97.5%, and the degree of freedom remains the same. All right, so if you see, this matches the result in the output. Similarly, we can calculate for beta 1. So let me quickly do that. So this is the coefficient plus standard error times t inverse probability 2.5%, and degree of freedom is 200 minus 2. And I'll copy this formula and paste it here, and here I just need to update the probability, and these two also match the output. So if you want a different confidence interval, for example 90%, I leave that as an exercise for you. You just have to adjust the probabilities in this equation. That's all for now. Thanks for watching. If you liked the video, please subscribe to this channel to get latest educational content on statistics, finance, risk management, and analytics. Also, if you are a finance professional and looking for a certification in data science, log on to peakstotales.com and check out our prep course for Finance Data Professional, which is a global certification offered by FDP Institute. Experience a new way of learning complex mathematical and statistical concepts with rich visualization in an easy-to-follow Microsoft Excel-based environment. Take advantage of our mind maps and Excel-based hands-on modeling sessions.